Flip-flop circuits are the circuits which we use to hold bits in one memory location's address. So mostly I've heard that these flip-flops are used in static memories. Oh, sorry, in memory inside processor. What do we call it? Cache memories. Flip-flops. Flip-flop SRs. SR as in set reset. An SR flip-flop is an arrangement of logic gates that maintain a stable output even after the inputs are turned off. So first you need to understand there are two types of circuits. These circuits are called sequential circuits. Sequential circuits for retaining data on bit basis in main memory. What are sequential circuits? Which actually use their output as input. The circuit that you have seen as of yet were taking input and giving output only. But these circuits are the kind which we can easily observe that the output is taken as input once again. Okay? These are called flip-flop circuits. Sequential circuits. These are called sequential circuits. S stands for set and R stands for reset. These circuits have two outputs, Q naught and Q. Q is the actual output and Q naught is futile, faltu as in Urdu. But what's the purpose? There is just one. Whatever the Q is, it has to be vice versa. If Q is 1, it has to be 0. Q is 0, it has to be 1. At any given time, if they both are the same, that means that there is an error. Computer does not allow these to become same in SR flip-flop. So we have got two types of flip-flops with NOR, not OR, and NAND, which is not AND. We know that this not OR and not AND circuits are actually what? These are universal gates. These not AND and not OR gates are called what? Universal gates. They have got this ability that we can use these two types of gates to form any logic circuit. Even they can form other gates. This universal power is actually utilized so many places. At so many places. For example, your um, USB flash drive. It is only made up of not AND gates. All right. So, anyways, we call it NOR active high. NOR active high means when we set, it is set, and NAND active low means when we set, it actually gets reset. So you would have to take care to remember set in terms of set. When Q is 1, it is only with not OR. And when we have set in terms of reset, it is only when S is 1 but the Q is not. So if we like to save a 0, we would have to make this S 1 in NAND active low SR flip-flop. So do expect that you may have any of these showing up, and you would have to remember these circuit shapes as well. Alright, and second thing that you have to actually understand that Q in NOR active high SR flip-flop is here, and Q in NAND active low SR flip-flop is here. Alright? Do remember these. So what is the purpose of SR flip-flop? Is to hold bits until the next bit is set. Alright? You would have to remember these shapes. And these truth tables are part. You don't have to solve it because solving it is tough. How would you come up with the equation? Just leave it. That's not part of the syllabus. So in not active high SR flip-flop, set is when we make S1 and R 0. Remember, we cannot change both inputs together, because if we change both inputs together, we would have same output here. So we do it one by one. So if it is set, S is 1 and reset is 0. Reset is when we make any register, any circuit, any input 0, it is called reset. And when we make it 1, it is called set. So as soon as we set, we find what? 1 at Q. So let's say when you like to, as an operating system, like to read a bit, where does it read from? At Q position. If at Q it is 1, it means in that bit 1 is saved. If at Q it is 0, it means that that bit is set to 0. So whatever in the form of registers or bytes, what you have been setting, what you have been writing is actually written this way throughout the memory. Let's say all those floating point calculations that you did this morning were actually being happening by computer this way. So set, and then we change this 1 to 0. As soon as we have 0 0 on both set and reset, whatever the previous input that is locked, that will be retained until the next change that occurs. You get that? If you want to lock previous inputs, you have to have 0 and 0. So it means that output will remain the same. We call it latch. Kundi laga di. Call it what? Latch. So when we are retaining, it is latch. When you like to reset, you have to make reset 1 and set 0. This will bring 0 here at Q, and Q naught will be obviously Q naught 1. And then you put a latch there as well, and that is again retain shift. You put 0 0, and whatever the previous input, it will be locked. In case if you put 1 1, you get what? 0 0 here, Q and Q naught, and that is called race, and that is an error. It becomes a bit changed, different when it comes to NAND active low SR flip-flops. When you set, it is reset. When you put 1 1, it is a latch. When you put 1 1 here, it is error. When you put 1 1 here, it is a latch. And then if you like to set, it would be making set 0 and reset 1, and then you set it, and then put 1 1, it is a latch, it retains. And similarly, the way we have 1 1 here for error, we have 1 1 here for retain shift. And if we put 0 0 here, which was retaining data here in NOR active high, in NAND active low, this is an error. Is it understood? Here on the right, when set is 1, Q is 0. Reverse, because the gates are changed. That is why it becomes a bit complicated there. I have not made it wrong. It is actually reset. Initial state here is set, here it is reset. But the input is same. Because of the change of gates, input is reverse. So what you use here to set is here to reset. What you use here to reset is actually to set here. What is an error here? It is retain shift here. And what is retain shift here? It is error here. It is actually opposite because of the change of the gates. Usually data input is made 1 bit by 1 bit. If done together, then error occurs. Alright? Is it clear? So what do you get? You may have definition of it, you may have how to make it, you may have a trace table of it, and you may have a question like, what is sequential circuit? Sequential circuit is circuit which actually uses its output as its input. Not all of them do it, only, well, I would say mainly circuits which are used to retain data in computer, maybe in RAM or maybe in cache memory or wherever. Such type of circuits are actually sequential. Because if the sequence is not there, they will not be able to carry on with the data which they have inside it. Because data passes on the circuit. So if it is passing the circuit, we have to take that output as input again. Is it clear? Where do we need sequential circuits? Mainly where we like to retain the data in memories. This is JK. J is in set, K is in reset. Jack Kilby was the person who improved upon this SR flip-flop for the reason that this SR flip-flop had one weakness, error. Remember, in NOR SR, 1 was error, and in NAND SR, 0 was an error. How to avoid that error? What he did over NOT and SR flip-flop, he put another 2 NAND gates and having a third input, which is clock. Which clock it is? It is the clock inside the processor, which is ticking as many times as the number of instructions which are being executed. Let's say your computer is of 3 gigahertz. It means the clock is ticking 3 billion times a second. This is what the clock is here. This is not the clock that you see in your system tray on the bottom right. This is the clock inside the processor. So what is happening now? 3 inputs. 3 input means that on your truth table you would have now 8 possibilities. But what happens that JK suggested that when the clock is high, not the low, when the clock is high, only that time the output generated is kept into kept so that we could make use of it, and whenever it is low, we are not going to use it. So only when the input at the time when the clock is ticking 1 or 0 is kept into consideration, otherwise it is left. So when the clock is low, we are not actually taking it into consideration anyway. So a JK flip-flop circuit is an improvement over SR, as it by including another 2 NAND gates in a high clock cycle, high clock, not low, overcomes SR weakness. What were those weaknesses? No race. SR has race. What is race? Second one was no limitations of individual input change. Earlier, it was said that not 2 bits can be changed. Now this time you can change 2 bits. it has another option to toggle the state. Toggle the state means if it is retaining 0, it would become 1. Toggle it. So when the clock is high, only those 4 considerations are there. When the clock is low, we are not going to do anything because it is not changing it. So J as in S set and K is in reset. So when you set, clock is set, although it is not AND gate. When you set, it is set. When you reset, it is reset. And now since you are allowed to change both bits, it is easier. If you want to toggle, you have to put 1 1. That toggles the state. If it is 0, it becomes 1. If it is 1, it becomes 0. If you want to retain, then it is 0 0. So this combination is coming from what? Not OR. SR. What is introduced? This was an error there in not OR. So remember, JK is actually exhibiting NOR SR. Only the difference is what was an error in NOR or SR has now the toggle thing here with an added input which is clock high. Clock lows are ignored there. Is it understood? Can we move on? Alright. Acha, in notes I have written so many types of flip-flop circuits. Only these two are mainly the part of your syllabus. SR and JK. People write. That is why I said that you should relate this JK with NOR SR. Yeah, still it has relation with that. The uh, truth table is like the one in NOR SR. Only there is one difference, that what was an error in NOR SR